Raman spectra general introduction. It is a special type of spectroscopy which deals not with the absorption of the electromagnetic radiation but deals with the scattering of light by the molecules. It is observed that when a substance, which may be gaseous, liquid, or even solid, is irradiated with the monochromatic light of a definite frequency mu, a small fraction of the light is scattered. Relay found that if the scattered light is observed at right angle to the direction of the incident light, the scattered light is found to have the same frequency as that of incident light. This type of scattering is called relay scattering. Professor C.V. Raman of Calcutta University, however, observed in 1928 that when a substance, gaseous, liquid, or solid, is irradiated with monochromatic light of a definite frequency mu, the light scattered at right angle to the incident light contain lines not only of the incident frequency but also of the lower frequency and sometimes of higher frequency as well. The lines with the lower frequency are called Stokes line, whereas lines with the higher frequency are called anti-Stokes line. Raman further observed that the difference between the frequency of the incident light and that of a particular scattered line was constant, depending only upon the nature of the substance being irradiated, and was completely independent of the frequency of the incident light. If mu I is the frequency of the incident light and mu s that of a particular scattered line, the difference delta mu is equals to mu I minus mu s is called Raman frequency or Raman shift. Thus, Raman frequencies observed for a particular substance are characteristic of that substance. The various observations thus made by the Raman constitute what is called Raman effect, and the spectrum observed is called Raman spectrum. Thus, in a simple way, Raman spectrum may be represented as shown in the figure. Explanation for observing relay line and the Raman lines. When the incident photon hits the molecule, this collision may be elastic or inelastic. Elastic collision means that the colliding particles will return with the same energy. Thus, the scattered photon has the same frequency as that of the incident photon. This explains relay scattering or the relay line. However, if the collision is inelastic, still the law of conservation of energy will hold good. That is, total energy before collision and after collision must remain the same. Thus, some energy may be transferred from the incident photon to the molecule so that the scattered photon has lower energy and hence lower frequency than that of incident photon. Thus, some energy may be transferred from the incident photon to the molecule so that the scattered photon has lower energy and hence lower frequency than that of incident photon. This explains the occurrence of the Stokes line. Alternatively, some energy may be transferred from the incident photon to the molecule so that the scattered photon has higher energy, hence higher frequency than that of the incident light. This explains the occurrence of anti-Stokes line. This explanation may be further elaborated as follows. When the photon strikes the molecule, the energy is absorbed by the molecule and it gets excited to some higher energy level. Now, if it returns to original level, it will emit the same energy as absorbed and thus we have relay scattering. However, in most of the cases, the excited molecule doesn't return to the original level. It may return to the level higher than the original level, thereby emitting less energy than absorbed. This explains the occurrence of Stokes line. Thus, this explains the occurrence of Stokes lines. Thus, a part of the energy of the incident photon remains absorbed by the molecule so that the molecule has higher Thus, a part of the energy of the incident photon remains absorbed by the molecule so that the molecule has higher energy than before. Alternatively, the excited molecule may return to a level lower than the original level. Thus, more energy is emitted than absorbed. This explains the occurrence of anti-Stokes lines. In this case, the molecule has less energy than before. The different case may be The different cases may be represented diagrammatically as shown in the figure. Levels have been shown equally spaced just for the sake of the convenience. Polarizability of the molecules and the Raman spectrum. The Raman effect arises on account of the polarization distortion of the electron cloud of the scattering molecule that is caused by the electric vector of the electromagnetic radiation. The induced dipole moment mu depends upon the strength of that is caused by the electric vector of the electromagnetic radiation. The induced dipole moment mu depends upon the strength of the electric field E and the nature of the molecule. We write mu is equals to alpha into E, where the quantity alpha depends upon the nature of the molecules and is called polarizability of the molecule. Thus, polarizability is the ratio of the induced dipole moment to the strength of the electric field. In case of atoms or spherically symmetrical molecules, spherical rotors such as the CH4, SF6, etc., same polarizability is induced whatever be the direction of the applied electric field. They are said to be isotropically polarizable. Such molecules are said to be isotropic molecules. In case of all diatomic molecules, homonuclear or heteronuclear or non-spherical molecules, non-spherical rotors, the polarizability depends upon the direction of the electric field. For example, in case of H2 molecule, the distortion produced is more when the electric field is applied parallel to the bond than when it is applied perpendicular to it. So we write alpha parallel greater than alpha perpendicular. Such molecules are therefore said to be anisotropically polarizable. Types of molecule showing rotational Raman spectra. A molecule spec A molecule scatters light because it is polarizable. Hence, the Gauss selection rule for a molecule to give a rotational Raman spectrum is that the polarizability of the molecule must be anisotropic. That is, the polarizability of molecule must that is, the polarizability of the molecule must depend upon the orientation of the molecule with respect to the direction of the electric field. Hence, all diatomic molecules, linear molecules, and the non-spherical molecule give Raman spectra. That is, they are rotationally Raman active. On the other hand, spherically symmetric molecules such as CH4, SF6, etc. don't give rotational Raman spectrum. That is, they are rotationally Raman inactive. These molecules are also rotationally microwave inactive. In fact, this is one of the reasons for the importance of the rotational Raman spectroscopy over infrared spectroscopy, because the latter requires that the molecule must have a permanent dipole moment, whereas the former requires that the polarizability of the molecule must change during the vibration. Explanation of Raman effect in terms of polarizability. The polarizability alpha of the molecule that is rotating or vibrating is not constant but varies with the frequency of vibration or rotation. It is sum of two parts. Equilibrium polarizability alpha naught, that is the polarizability when the atoms of the molecule are in their equilibrium position. Second, the sum of polarizability of the molecule due to the various rotational and the vibrational motion, each term depending upon the frequency of rotation or vibration. Thus, alpha is equals to alpha naught plus summation of delta alpha n divided by delta r into Rn cos 2 pi mu n t, where alpha n is the polarizability associated with the nth rotational or vibrational mode and Rn is the maximum displacement of the atom involved. Further, the electric vector of the electromagnetic radiation varies with the time in sinusoidal manner. E is equals to E naught cos 2 pi mu naught t. Substituting the value of the alpha and E from the equation second and third in equation first, we get mu is equals to E naught alpha naught cos 2 pi mu naught t plus summation of delta alpha n divided by delta r into r n cos 2 pi mu n t cos 2 pi mu naught t further equals to E naught alpha naught cos 2 pi mu naught t plus half E naught summation into delta alpha n divided by delta r Rn into cos 2 pi mu naught minus mu n into t plus cos 2 pi into mu naught plus mu n into t. This expression consists of three terms. The first term has the frequency of the incident radiation and represents relay scattering. The second term, mu naught minus mu n, represents Stokes line, whereas the third term contained mu naught plus mu n represents the anti-Stokes lines. Quantum theory of pure rotational Raman spectra of diatomic molecules. The selection rule for pure rotational Raman spectra of diatomic molecules are delta J is equals to 0, comma, plus minus 2. The selection rule delta J is equals to 0 corresponds to the relay scattering, whereas selection rule delta J is equals to plus minus 2 give rise to the Raman line as explained. We know that the energy of a rotational level with the quantum number J is given by mu bar is equals to Bj plus 1. When a transition takes place from a lower rotational level with the quantum number J to a higher rotational level with the quantum number J dash, the energy absorbed in terms of the wave number will be delta mu bar is equals to Bj dash into J dash plus 1 minus Bj into J plus 1. For the selection rule, delta J is equals to plus 2, that is J dash minus J is equals to J or J dash is equals to J plus 2. So we get delta mu bar is equals to B into J plus 2 into J plus 3 minus Bj into J plus 1. So the here comes out is equals to b into 4j plus 6, where j is equals to 0, 1, 2, 3 and so on. Again for the selection rule, delta j is equals to minus 2, that is j dash minus j is equals to minus 2 or j dash is equals to j minus 2. So we get delta mu bar is equals to bj dash into j dash plus 1 minus b into j dash plus 2 into j dash plus 3 is equals to minus b into 4j dash plus 6 is equals to, whereas j dash is equals to 0, 1, 2, 3 and so on. Combining the results of the equation 3rd and 4th, the wave number of the lines obtained in the Raman spectra will be given by mu bar is equals to mu I bar plus minus delta mu bar. Mu bar is equals to mu I bar plus minus b into 4j plus 6, where j is equals to 0, 1, 2, and 3 and so on. Here, mu bar I represents the wave number of the relay line. Plus sign give lines with the higher wave number called the anti-Stokes line and the minus sign give lower wave numbers called Stokes line. From equation fifth, it may be seen that for the j is equals to 0, mu bar is equals to mu I bar plus minus 6b, that is the first stroke, and the anti-stroke line will be at a separation of the 6b from the relay line. Further putting j is equals to 1, 2, and 3, the separation between any two adjacent stroke line or anti-stroke lines will be 4b. Thus, the pure rotational Raman spectra expected for a diatomic molecule may be represented as shown in the figure. Intensity of lines of the pure rotational Raman spectra. As explained earlier, the intensity of lines depend upon the population of the initial level from where the molecule are excited or de-excited to the final level. Since the population of the rotational levels as shown in the figure, therefore the intensity of the strokes and the anti-stroke lines vary in a similar manner. Now the application of pure rotational Raman spectra. From the pure rotational Raman spectra, noting the separation between the lines, the value of the B can be obtained from which the moment of inertia and the bond length of the diatomic molecules can be calculated as explained earlier. Quantum theory of rotational vibrational Raman spectra of diatomic molecules. For large molecules, the line obtained due to the rotational transitions are so weak that the beyond the resolution. Hence, we have pure vibrational Raman spectra for which the selection rule are same as for the pure vibrational spectra discussed earlier. However, in case of diatomic gaseous molecule, the resolution of rotational fine structure is sufficient and can be studied. Thus, diatomic gaseous molecule give rotational vibrational Raman spectra which can be explained as follows. The selection rule for the transitions are delta mu is equals to plus minus 1, whereas delta J is equals to 0, plus minus 2. However, at room temperature, as most of the molecules are in the lowest vibrational level, that is mu is equals to 0, therefore the significant vibrational transition is from mu is equals to 0 to mu is equals to 1, called the fundamental vibrational transitions. Restricting ourselves to this vibrational transition only the results obtained are as follows. For delta J is equals to 0, delta mu bar is equals to omega E into 1 minus 2 xe called Q branch. For delta J is equals to plus 2, delta mu bar is equals to mu E 1 minus 2 xe plus B into 4J plus 6 called S branch. For delta J is equals to minus 2, delta mu bar is equals to omega E into 1 minus 2 xe minus B into 4J dash plus 6 called O branch. Representing the values for the Q, S and O branches by the delta mu bar Q, delta mu bar S and the delta mu bar O respectively, and the wave number for the exciting radiation by the mu I bar, the wave number of the stroke line will be as follows. We have considered the case for only delta mu is equals to plus 1, which represents stroke line. The anti-stroke line are those which have delta mu is equals to minus 1. They are usually weak because very few molecules are in the excited vibrational state initially. The rotational transition accompanying the vibrational transition from mu is equals to 0 to mu is equals to 1 and the rotation vibration Raman spectrum obtained may be represented as shown in the figure. Advantages of the Raman spectroscopy over infrared spectroscopy. Raman spectroscopy has a number of advantages over infrared spectroscopy as briefly explained below. First, since Raman frequency are independent of the frequency of the incident radiation, hence by suitably adjusting the frequency of the incident radiation, Raman spectra can be obtained in the visible spectrum range where they can be easily observed rather than more difficult infrared range. Second, Raman spectra can be obtained even for molecules such as O2, N2, Cl2, etc., which have no permanent dipole moment. Such a study has not been possible by the infrared spectroscopy. Third, Raman spectra can be obtained not only for gases but even for liquid and solid, whereas infrared spectra for liquid and solid are quite diffuse. Because of the ease with which the Raman spectra can be studied, the molecular structure of large number of compounds have been determined by the Raman spectroscopy. However, infrared method still continues to remain popular. Experimental arrangement for Raman spectra. This is the experimental arrangement for observing the Raman spectra is shown in the figure. The fraction of the light scattered is so low that normally every week Raman lines are observed. Hence, to detect these lines, it is necessary to use a powerful source of incident light. Earlier, mercury vapor lamps were used, which gave an intense monochromatic radiation of wavelength 4358 angstrom. However, with the development of the lasers, which are very powerful sources of the monochromatic radiation, Raman spectroscopy has been greatly revolutionized.